Good morning, pre-calculus class. This is obviously a recorded lecture on chapter 14. This will be the last chapter that we're going to do this year. If we pull up your class page, you'll note, again, here we are, C period, B period is the same. I've added a new topic page. And this is going to be entitled Chapter 14 Material. And the first thing on here is this anticipated timeline again. It says the last 6 weeks of the year. Obviously, we're sitting down here now on May 10th, 11th. And you had your chapter test on Tuesday. For all the conics, we're starting section 14.1 today, limits graphically and numerically. We'll also be looking at one-sided limits, which the schedule says we do Friday, but I think it makes sense to do both of these at the same time. So let me go back to here. I want to start this by looking at something that you had way back in September. This is from your very first test back in the third week of September. And this was a graph of a piecewise defined function. It had various line segments and holes and points sort of floating around somewhere. And you were asked to find, for example, in number 16, g of 1. G of 1. Now, how do we do that, and what does that have to do with limits? You'll see very, very closely. Now remember, the y is the g of x. So in this formation here, the 1 is the x value, and the entire expression, g of 1, that's going to be the y value. So to figure out what g of 1 was, what you did was you looked where x was 1, that's right here, and then you looked where the point was, and the point was up here. Notice there's a hole here, hole. And the g of 1 problem was correctly answered as 3. Okay, so that was this type of find the functional value if I give you the x value. Okay, so likewise, if we just knock out 17, 18, 19, all of these are very quick and easy problems. I'm telling you the x value. So here's 17, g of -2. So we go to where x is -2. Let me do this in a different color. -2. And we're looking for where's the point in this area. And the point is right there on this line segment. And so that worked out to be -2. The y value was -2. In fact, if I asked, what are the coordinates of that point, it would be x is -2 and y is -2. Okay, so that was that one. Let's clean this up a little bit and go to problem 18, find g of 5. So once again, here's 5. And notice there's a hole here. That's not a point. That's a missing point. But we do have a point here. And the coordinates of that point, x is going to be 5, and y is -1. So that's a pretty straightforward problem. And lastly, g of -6. This is probably the most interesting of these 3 questions, g of -6, or 4 questions. We go to where x is -6, which is right here, and we're looking for where's the point, and I see no point. Notice this is not a point, not a point. In fact, it's a missing point. So the way this was answered, g of 6, you probably scratch the equal sign and write is undefined. Okay, so there was no defined value at x is equal to -6. Okay, also on this page was a series of problems about solving equations. We're not going to do a lot of equation solving in chapter 14, although I think it's worthwhile, especially since you have your final exam in 2 or 3 weeks, that we look at this, solve for x. This is problem number 20. G of x is 0. Now notice again, if I write g of x is y, I'm telling you what the y value is. Y is 0, but you don't know what the x is. So you have to come up with the x value that gives you a y value of 0. One way of thinking about this is to figure out where y is 0. That's this horizontal line. Y is equal to 0. And put your eyeball right there. So here's an eyeball with little eyelashes. And if you look along that line, y is equal to 0, I see the graph hitting that horizontal line in a couple of places. There's a point here, and there's a point here. So in fact, there are two different x values that have a y value of 0, and equations can have more than one solution. So x is equal to -4, or x is equal to, let's say, 1, 2, 3. Okay, so that would be how you solve that equation. And we'll do one more over here in green. Solve g of x is 1. Again, we sort of do the same thing, except now our eyeball is moved up to where the y value, remember, this is the y value here, is equal to 1. So now we're up here at this horizontal line. And we imagine sort of sighting along that line. There's my green-eyed monster. And we see a couple of points. One is here, and the other one is right here. Okay, and we need to identify those x values. So x would be -3, or x is equal to, what's that, 4, 1, 2, 3, 4. Yeah, so those are the solutions to those two equations. Now, sometimes, as you're aware, equations do not have solutions. So just be aware of that. Just like in problem 19, we had an undefined value, undefined. In equation solving, we often have, or sometimes have, equations that do not have solutions. So let's see. Let's look at this equation right here. Solve for x. G of x is equal to 2. So again, this is the y value, and we're trying to figure out what the x value is. So what x value gives you a y value of 2? Well, just like in the previous equation, you can imagine looking at the line y is equal to 2, and put my eyeball there. And as I look along this line, I see no point. There is no point on the graph with a y value of 2. Notice this is not a point, not a point. So this equation, solve the equation for x, g of x is 2. You would write there is no solution. No solution. And it would be wrong to say undefined. That's not what I'm asking. I'm not asking, is the function defined at 2? And in point of fact, the function is defined at 2. Right there. I see a point where the x is 2. The y happens to be -1. This question is asking, if the y is 2, what is the x value? And there is no defined x value. Or there is an x value of, well, there's x values for lots of things. We might even want to look at the domain. The domain looks like we got x's all along here. In fact, this function is defined for all x values greater than -6. I mean, I could pick any number from -6 up, okay? And I would see a y value at every one of those x values. There's an interesting jump here. The graph jumps from that location down to this location. And there's sort of a point missing here, but there's still a defined y value when x is 1. And as we go out to the right, you can see that the function is defined for all x's. At -6, the function is undefined. Okay? So yeah, this particular equation has no solution. Okay, hopefully that got your brain back into the idea of looking at graphs. This was another set of questions that were on your semester exam, very similar, except it was multiple choice. And we had this strange function that had various pieces to it. Let me sort of emphasize that this was a dot. This was some sort of vertical asymptote here. This was an open hole, no point there, and there was a point here. And there was a point here with an open hole there. And there was a point here and an open hole here. Okay, so you might remember this from, there was an open point there. You might remember this from January, or I guess it was right before Christmas, December. This was our final exam, and again, you were asked to do things like evaluate the function. Okay, so this is an evaluate the function problem. I give you x is -1, and you had to determine y. Here, I gave you y, okay, so y is 0, and you had to solve for x. So if we just sort of do the same little exercise that we did on the previous screen, this says x, problem number 57 here, x is -1, so you go to where x is -1, which is right here, and you look at the point, and the point is up there at 2. Okay, so that's the way you did that. At 58, we were trying to solve the equation. F of x is 0, so we put our eyeball on the 0 line, and we look and we see whether or not we have any points. There's no point there. Nope. There's no point there. Nope. But there is a point here. Okay, so the curve is crossing the x-axis there, and that was at, let's see, 1, 2, 3, 4, 5, 6. So x had to be 6. Okay, and again, let's just do 2 more like that. 59, notice that it's again a solve an equation problem. I tell you that y is 1. So at 1, you would be looking at the graph, and if you look at the graph at y is equal to 1, it's pretty clear that there is no dot there. So this is the 1 level right here. As we go out, there is no part of the curve at all. So this particular equation had no solution. Okay, no solution. And for problem 60, f of -2, we had to go where x was -2, which is right here. Remember, this was a point and this was the hole. Okay, and f of -2 was 2. Okay, so that's the way you answered those. You might want to note that one of the choices here was this D and E, and I never did tell you what that meant, although that's what we're going to study in chapter 14 on limits. Now, D and E stands for does not exist. Okay, so a little bit on what we've done in the past, and now let's go to what we're trying to do here. We're talking about limits, and we actually saw limits at one point when we were doing the trigonometry test. Let me pull that up. Let me pause this just for a second. Okay, so what I've done is I've pulled up your test on graphing. This was the trig test on graphing. And we noted that there were some problems, 7 through 10, that asked questions like this. Well, we never did actually have the notation yet, but this was asking as x, let me write that up here, as x approaches pi, and then there was a little superscript plus sign, and you had to determine what was the cotangent of x getting close to. That was the question. The whole idea of limits is this type of question. Let's see, so how did we do this way back when we did trig? The first thing we had to do was we had to look at the correct graph, and the cotangent graph was this one here. And then we had to find pi in the picture, and it was sort of hard to see. It's certainly hard to see here, but this was pi right there. That was the value pi. And this question said x was getting close to pi from the right side. So you thought, let's see if we can draw another picture over here. Here's pi. Let's see, hold on a second. Okay, so yeah, this was a vertical asymptote at pi. There was a vertical asymptote at pi if you had the graph. And the curve was going like this to infinity. And the way we thought about this problem was if considering x values getting closer and closer to pi, so think about x moving this way, what was the curve doing? And as x moved to the left, the point was going up. And in fact, it was going higher and higher and higher. So the correct answer for this was, as x approached pi from the right side, the cotangent of x was getting really large. So you could write plus infinity or just infinity. And that was a limit type of problem. One more example quickly. This was another limit type problem, even though we didn't use the terminology. This says, look at the cosine graph, which is pretty easy. That's this one right here. Here's the cosine graph. You should certainly recognize that. It's a wave. And it says, as x approaches negative 2 pi from the right. Okay, so here's negative 2 pi. And again, I think maybe a larger sketch of this would be useful. So here's our cosine graph. Remember the cycle or the period is 2 pi. So that's one cycle, and we have a similar cycle over here. This is negative 2 pi. And the question again was, as x approached negative 2 pi from the left. So x is coming in this way, getting closer and closer to negative 2 pi. Oh, sorry, coming in from the right. That's a little plus sign up there. Okay, so as x approached negative 2 pi from the right, what did the cosine of x do? And, what was it getting close to? And again, you can sort of think of a point moving on the graph. As x was getting closer and closer to negative 2 pi, this point kept rising higher and higher and higher and higher. And in fact, when you got to negative 2 pi, the point was exactly right there. It was exactly at this height, which was 1. And that was the answer to this problem. As x approached negative 2 pi from the right, the cosine was approaching 1. Okay? Now, let me go back and look at these previous graphs that we were messing with. And I want to do a similar type of limit problem. Let's look at this one for a second. This was a hand-drawn graph, and it was pretty clear where the holes were and where the points were. This is a function called g. Okay, so suppose I ask, just by looking at this, as x approached, let's say 1, as x approaches 1, what was g of x getting close to? So that's sort of a question there. Okay, now this was the notation we had way back in chapter 1. In chapter 14, we have special notation for this same thing. We use LIM, which stands for limit, and instead of writing as x approaches 1, underneath the LIM, sort of a smaller subscript type thing, we say x goes to 1. And then instead of the comma with g of x equals, we simply write the limit of g of x as x approaches 1 equals what? Okay, so this one expression is the same as this, what we would have done way back in chapter 1. Okay, so let's see. What happens to g when x gets close to 1? Now, there's an important note here, and I think you need to listen to this carefully and write down in your notes what this means. This, find g of 1, and this, the limit of g of x as x gets close to 1, are different problems. Different problems. And that's really important because, in fact, they have different answers. Okay, so let's go back and just review again. This green one says, what is the y value when x is 1? And to do that, you have to look at the graph where x is 1 and find a point that happens to be right here. And that's the ordered pair 1, 3. Right? So when x is equal to 1, g of 1 is equal to 3. And again, we did that 10 minutes ago. I'm emphasizing now that that is how you find a functional value. X is 1, and the y value happens to be 3. Okay, fine. Let's go to the limit problem. Here's the most important thing on limit problems. This does not say x is equal to 1. And in fact, we don't care what x is. All we care is x is getting close to 1. So here's one way to think about it. Suppose I could somehow block from view what happens. I'm going to just sort of shade all this away. This is gone. So you have no information at all about what happens when x is equal to 1. So this sort of shaded area is blocking the graph when x is 1. This is like x is equal to 1 is unknown. Well, if I were trying to solve this problem, I can't do it because I don't know what happens when x is 1. I've blocked it from view. However, the limit problem is exactly solvable. You can do this very, very quickly and easily. This says, what happens to g when x gets close to 1? Okay, so what do I mean by that? Well, if we start to, this is 1 right here, right? Think about x values as you get closer and closer and closer to 1. And look at the graph, and you'll note that as you get closer and closer to 1, the graph is dropping, 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 dropping. It seems to be getting close to this value right here. Well, let's get close to 1 from the other side. As we get closer and closer to 1 from the left, here's our x is going that way, and the y values are here and here and here and here. And in both cases, we seem to be getting closer and closer to this location. Now, so what location is that? Well, by looking at the scale on the y-axis, it's pretty clear that this is equal to -2. And that's the answer to that limit problem. As x approaches 1, now let me take away all this shading here. As x approaches 1, g of x approaches -2. Now note, and again, what happens when x is equal to 1 is irrelevant to the limit. We don't care what happens when x is equal to 1. For the limit problem, it's only what happens when x gets close to 1. Okay, that's the main idea. Let me try another limit problem. This time I'm going to get close to 5. Okay, so this blue one we did was what happens when x gets close to 1. And now I'm going to ask, what's the limit when x gets close to 5? Okay, so what's the limit when x gets close to 5 of this function g of x? And the question is, what's going on? Well, notice that at 5, this was 5 right here, we had this sort of a jump. The graph down at this location, this was the ordered pair, 5, comma, -1, that was the ordered pair. And up here we had a hole. If I said, where is the hole? I suppose you could say it's at the location 5, 2, but there's no dot there. There's a missing point. There is no functional value at 2, right? The y value is not 2. In fact, the y value is down here at -1. Now, if we were to ask, what is the y value when x is 5? That's the easy problem. That's this one. Remember, g of 5, that was -1. You just look and see where the dot is. The limit problem is more enticing. So for the limit, we don't care what happens at 5. In fact, I can block that information from view. So pretend this is no longer visible. I do not know what happens when x equals 5. All I'm asking what happens to g when x gets close to 5. Okay, now we sort of have a dilemma. If we're coming in towards 5 from the right, this would be this type of notation, x approaching 5 from the right. If we're coming in from the right and we're sort of looking at the graph, we note that, okay, the y value is there, and then there, and then there, and then it starts to go up, goes up, it goes up, it goes up. It looks like as we get really close to 5, we seem to be getting close to this location. Okay, and we would have to look at the graph and say, that's over there at -1. Ooh, but what happens if we get close to 5 from the left side? Okay, so now we're coming in this way, and we're trying to figure out what's happening to the graph, and you go, okay, well, there's a point here, there's a point here, there's a point. The graph is obviously increasing. We're rising, we're rising, we're rising. We seem to be getting close to this value. Okay, so what's that value? And that looks like it's 2. Well, we have a problem here. The graph is not getting close to a particular y value. In fact, it seems to be getting close to 2 different numbers. If we come in from the left, the graph is approaching 2. If we're coming in from the right, the graph is approaching -1. In this case, we say this limit does not exist. Okay, so we can say does not exist. In order for a limit to exist, the function has to be getting close to a single value, to a single number, like what happened here. Well, remember when we were approaching 1, the function was getting close to -2, and that was fine. That was the answer. Now, even though the limit of g as x approaches 5 doesn't exist, we do have things called one-sided limits, and you could sort of imagine what's going to happen here. What happens to g of x when x approaches 5 from the right side? Okay, now we don't care about what happens from the left. All we care about is what happens when x approaches 5 from the right side. Now again, this information is still blocked from view. Okay, so I don't know, but now I actually don't care what happens about g as x approaches from the left. Let me see if I can bring over a screen. Okay, so what I brought is my screen shade tool here. And because this limit problem says x is approaching from the right, I really don't care what happens from the left. Let me just block that from view. Okay, so I don't have any of that information at all. All I do have is this. And again, let me just bring this in a little bit more. Okay, so this screen is cutting right off at 5. And as x approaches 5 from the right, you can sort of picture x values coming in and looking at the graph. Okay, we're down here, we're down here, we're down here. Now we're rising, we're rising, we're rising, and we're going to this level. So what level is that? Well, again, by looking at the scale, it was pretty clear it was at -1. Right? So remember, it was at -1. Now, the fact that there's a point there is irrelevant. I don't care that g of 5 is -1, but I do know the limiting value is, in fact, -1. Let's try coming in from the other side. Let me move my screen to the other side, like this. Okay, so now the question is, what happens to g when x approaches 5 from the left? Okay, so this is the way the problem would be stated. What's the limit of g of x as x approaches 5 from the left? That's the question. Okay, so again, we're thinking, we look at the graph, we're thinking we don't care what happens at 5. What happens at 5 is irrelevant. I'm not asking what is g of 5. I already know that answer. G of 5 happens to be -1. This is asking what happens when x gets close to 5 from the left side. So let me just sort of block off from view everything that happens from the right side, and all I care about is what happens when x gets close to 5 from the left side. Okay, so this was 3, this is 4, and 5 is right in there. Okay, so now as you get closer and closer, as x is getting closer and closer to 5, coming in from the left side, the points are obviously rising. Right, so we're going higher and higher and higher, and we seem to be getting close to this level, and that level is 2. The limit of g as x approaches 5 from the left is 2, one-sided limits. Okay, so we have a couple of things going on there. We do have one-sided limits, and we have just regular limits. This is our regular limit. The limit does not exist because the graph is going to 2 different levels, and in this case, we have the limit from the left of g of x does exist. It happens to be the number 2. And the limit of g of x as x approaches 5 from the right. This is the right-hand limit that does exist. That happens to be -1. Okay? Good enough. Let's just do one more quickie looking at this picture, and then we'll go look at the other picture, and then we'll look at the textbook. Okay, so let's see. Let's go over here and go again to this jump. This is a jump right here. When x is equal to -3, something interesting happens. So I might ask, what is g of -3? That's not a limit question. That's just look at the dot. I might ask this question, what's the limit of g when x approaches -3 from the right? What's the limit as x approaches -3 from the left? Still looking at the function g. And lastly, what's the limit of g of x as x approaches -3, taking both directions into account? Okay, so we have like 4 related questions here, all looking at function g and what happens when x is around -3. Okay, so now the first one is pretty straightforward. It says x is equal to -3. Where's the dot? There's the dot. Answer is 1. Done. That was way back in September. Now the new material. Second question, what happens when x approaches 3 from the right? So you have to think of x values, approaches -3 from the right. So we're coming in here like this. We're going along the x-axis, getting closer and closer to -3, but not getting to -3. I don't care what happens at -3. I'll sort of block that off. As x is approaching -3 from the right, the y values are down here, and they sort of stay right there, and they're always hanging right around -2. That's the answer. Okay, how about when x approaches -3 from the left? Now we're coming in from the left side, so think of x values like this, and sort of observing what happens to the y values. The y values are rising, they're rising, they're rising, they're rising, and they're rising up to this level, whatever that is. Oh, that's 1. Okay. So now we have a right limit and we have a left limit. How about the limit? In order for a limit to exist, in order for this to be a valid answer, the function has to go to one level only. And this function seems to be going to 2 different locations, right? As you come in from the right, we're down here at -2. As you come in from the left, we're up here at 1. Okay, because the function is going to 2 different levels, this double-sided limit, if you want to say that, or the limit, does not exist. Does not exist. Okay, so that's a whole graphical approach on dealing with limits. Let me pull up my clock here, 35 minutes. Okay, what I want to do now is to have you work with a partner. I've got a practice sheet, if you will, where you're going to be looking at pictures and doing 2 things. You're going to be trying to solve equations, not solve equations, find functional values like that. In fact, we're going to sort of scratch the solve equations for today. But you're going to look at, find the functional value. I tell you what x is. But then you're also going to do a whole bunch of limit problems. Okay, and in the limit problems, again, you have to be a little careful. Whatever the function is, x may be getting close to this x number, say from the right side, or from the left side. Could be getting close to a from the left side, in which case you're dealing with a one-sided limit. Or if I don't have a plus or minus there, and I say x is getting close to a, you have to consider both the left and the right direction. Okay, so let me go ahead and stop the recording. Your substitute will give you a worksheet. We've got about 10 minutes to play with this. Get as much as you can do tonight, or get as much as you can do right now in class. Finish it tonight, and then I'll post all the answers to these so you can check yourselves. And tomorrow we'll do the calculator investigations. Right now we're just looking at pictures. Okay.